Well, electrochemical cell, electrochemical. So this Mx is ionic conductor. Means no electron transfer. And the cathode, MXY, has a mixed conductor. Both electrons and ions conducting. Okay, so now at the anode interface, we're going to have M plus ions traveling through the electrolyte, and at the MXY cathode, the M is going to diffuse according to the fixed first law, and then electron is going to be supplied through the outer circuit, and electron is going to be transferred from through the outer circuit. Let me just draw. This is the outer circuit, okay? So at this interface, we have M is going to M plus E electron. And at this interface, we're going to M plus electron M. Okay? And this is the chemical diffusion according to the fixed first law. And this electrochemical cell has an EMF like activity of electroactive species in the cathode and in the anode, and we call this Nernst equation. Now we are going to make a electrical circuit analogy for this whole reaction. So before we do that, let me just arrange the terms here, electrical circuit analogies. Now, this is electron transfer and the resistance. And the other important thing is the capacitor, and that is electron accumulation. Happens in this capacitor. So types of electrochemical cell. First M and MX and M. Both anode and cathode are the metals. Let's suppose this electrochemical cell, and what's going to happen in this case. We call this a symmetrical cell, non-blocking electrode. Okay. And in this case, the electrical analogy, circuit analogy, is going to be just the resistance, like this. Okay? That's the top one. And the second type, maybe one side is metal and the other side is MX, electrolyte, and the other side is a ionically blocking electrode, like a graphite. Okay, let's suppose this is a lithium, and this is a lithium electrolyte, and then we have a graphite, something like this. Okay, that is ionically blocking electrode. All right. Then what we can see here is that we are going to have a polarizations like this, and then of course the electron can be supplied to this M plus ion through this ionically blocking electrode on the other side, so that it can be neutral, but this neutral ions cannot penetrate into this ionically blocking electrode, so that it's going to be plated. We call this electroplating. CF electroplating. All right. Then the circuit is now going to be the electrical circuit analogy is going to be the resistance and the interface capacitance, and then this whole thing is the geometric capacitance is going to be connected in parallel. So here the RB is bulk resistance. For ionic transport, CI capacitance due to double layer CG. And then the third type is going to be called Debye circuit. Which has been developed in 1920s. Okay, that is the electroactive species, electrolyte, and the mixed conductor now. This is not ionically blocking. This is ionically conducting, mixed conductors. Here we have MXY. It's going to be a mixed conductor. Chemical diffusion of M happens inside the materials. Now in this case, the analogy is now going to be this, which is the same, and the capacitor Ci and Warburg impedance is newly introduced here. And then this whole thing is again geometric capacitance is in the parallel, like this. Okay? So the basic idea of the AC impedance analysis is that we can develop the electrical circuit analogies to the real system, and then with the AC impedance spectrum, we can separate each values. Okay, and then we come to know what is the bulk resistance, what is the double layer capacitance, and what is the Warburg impedance, for example, and what is the geometric capacitance in the system. And if we come to know these values, then we can have a good, very important idea how to develop the new battery system, new electrochemical system. If any of these values is abnormally high, then we have to find a way to reduce that, to activate or enhance the electrochemical reactions of the electrochemical cell, which is related to the charge-discharge capacity as well as the charge-discharge time, required time for that. Okay, that's a very essential thing. So this AC impedance spectrum is a very important thing that we have to analyze in every electrochemical cells. Now, for that, let me introduce the basic electrodynamics. Okay, electrodynamics. Now, impedance. Since the capacitor is included in the whole circuit, we have to play with this impedance and admittance thing. Admittance. In a DC, it is related to the resistance and conductance. Okay? We apply AC voltage with a certain frequency and want to measure G star here and or Y star as a function of frequency. Which is 2 pi f angular frequencies. So what's going to happen is that we have a metal here, then the oxidation reduction reaction happens at this interface, and at this interface also we are going to have oxidation and reduction process according to the frequencies that we apply between those two electrodes, all right? So today, let me just to give you the basic ideas what's going to happen in this electrical circuit. First, the total impedance of a series combination of impedances is the vectorial sum of the individual impedances. Simple as that. Series combination. Total admittance of a parallel vectorial sum easily be translated to one another. Okay, let's see the example. If we have series combination of capacitance resistance like this, then we can see the Z star impedance R plus JX okay. R is and if we have a parallel combination of then we have admittance and then G is conductance. Which is 1 over R, and B is C. Now, we know this admittance is reciprocal of impedance, which is R plus JX, R minus JX over R square plus X square. And then that's going to be R over R square plus X square minus JX over R square plus X square. And Y stars can be represented with a conductance and a susceptance. This conductance now becomes R square plus X square. B is minus X over R square plus X square. It's just a simple mathematics, okay? Yeah. Now, if we really get into the electrochemical cell analysis, let's just mention about the assumptions that we have to make. Okay, assumptions. General assumptions. Well, this is the general assumptions, but it has to be kept in mind because in most of the experiments, these facts, if you do not confirm these facts, then your experiment is going to go wrong. Okay, you are going to have totally wrong numbers, totally wrong experiments, and sometimes. 1 year experiment is just becomes useless after you realize the fact that your cathode or anode or your electrical lead, okay, is going to react with electrolyte or something. If you find that later, after the 1 year experiment, sometimes it really happens. And then the data you have taken for a year is everything is wrong. You cannot, it becomes useless. So it is very important to confirm these assumptions. So you have to do the experiment very carefully. Now let me try the simple cells in a series of connections. And we know the jet star impedance is going to be Jx, and then that is J omega c, okay? And if you plot minus x and r, then you see you change the frequency, you're going to have a straight line there. You see, this is the plot r versus x. With changing frequencies. And R is not a function of frequencies because it's the DC component, and minus X is going to be 1 over omega C. So as you increase the omega, the minus X value is going to go down. So as you increase the omega values, the X is going to go down like that. And the impedance, which is 1 over G star, plus R minus J omega C, now is equal to omega C over R omega C minus J, and then omega square C square J omega C R omega C square plus 1. Now that is going to be G now is equal to R C square R C plus 1, and B is 1. G So, if you plot B and G, okay, now in this case, you're going to have a semicircle here, and the frequencies, you increase the frequency in these directions. And then, according to this equation, you're going to see that the maximum point here is 1 over 2r, okay? And then here, that is 1 over r. The r is the resistance, bulk resistance of the system, right? And here, 1 over 2r is radius. Okay, G equal to 1 over 2r, B equal to 0. So with the minus x and r, we just have a straight line and we don't get the information, proper information with this. But if we plot that with the B versus G here, yeah, the susceptance and the G values, then we are going to have a semicircle here, and then with this we can have important information out of this. So at maximum point, B equal to G, okay, R omega C so R omega C equal to 1 at the maximum point, okay? And the capacitance now are omega. So we can separately determine the value of R and value of C in the circuit knowledges that you had. Okay? And we can develop the same thing for the case where we have the circuits and the resistance and the capacitance in parallel. And in this case, we can say it like this, okay? In parallel, the admittance now is going to be sum of each component. And we continue the analysis of the second case in the next week on Monday. All right.